Hello, my name is Francesco Luzi, and I will be presenting Segment Anything from space. Segment Anything model, or SAM, is a model developed to segment images from a number of different input prompts. Two possible example input prompts are a bounding box and a single point prompt, shown below. A single point can be used as an input where the model attempts to segment the object the point is referring to. In this case, that is a solar panel, shown here. Since a point can refer to multiple objects, SAM produces three masks at potential outputs. A bounding box can also be used as a prompt where the box completely encapsulates the object of interest. In that case, only one mask is generated because there is no ambiguity in what the model should segment. In our work, we only use these two types of prompts. SAM demonstrated great promise for use in zero-shot segmentation and human interaction annotations for natural imagery, but SAM was not tested on satellite data and very little overhead imagery was used, so it was left unclear whether SAM would generalize this kind of data. Satellite and high-altitude overhead imagery possesses unique challenges to segmentation that isn't normally present in natural imagery. Here's an image taken from a popular dataset COCO, and here's an image taken from an INRIA dataset. We investigate to determine if SAM, trained on natural imagery like on the left, would generalize well to overhead imagery such as is shown in the right. We evaluate the performance of SAM on several large and diverse overhead segmentation datasets. We use a solar panel dataset, 3 building datasets, a cloud dataset, a road segmentation dataset, a crop boundary dataset, and a land use dataset that we split into 3 datasets by land type class. Each dataset is between 0.3 and 0.5 meters per pixel, with the exception of 38 cloud and parcel delineation datasets, which are 30 and 10 meters per pixel resolution. In the SAM paper, the authors demonstrate SAM's usefulness in automatic zero-shot segmentation by providing single-point prompts in unseen datasets and showing the model's ability to generalize to unseen data. We emulate their experiments with overhead imagery to understand SAM's ability to generalize to unseen overhead data. We also provide output to SAM from a trained model to determine if SAM can improve on a fine-tuned model's output without observing any of the data. For our experiments, we use 3 different prompt types. Single point prompts taken from the ground truth of the image for each object segmentation mask. We do this with a randomly selected point in the object mask and a point selected at the center of mask for our 2 different prompt types. We also retrieve bounding box declarations taken from the output of a pre-trained UNet model as input for SAM. These prompts, along with the image, are given to SAM, and SAM produces either a single mask for the bounding box prompts or 3 masks for the single point prompts. Of the 3 masks, we select the one that the model is most confident in. The results show that for most datasets, SAM performs relatively well considering it hasn't seen data of this kind, but it still falls short of a properly trained model. In the light gray, we have the UNet results reported in each dataset paper when they were available, and in dark gray, we have results for our fine-tuned UNet model. As you can see, the single point prompts always performs worse than the fine-tuned model, and normally performs similarly to each other, with center point having a slight edge over random. We also see that SAM, using the output from a UNet model, generally performs slightly worse, with the exception of the deep globe land use, where it improved upon the UNet segmentation for the land and agricultural classes. Overall, SAM performed fairly well given the limitations in its training data. Here we show several select datasets with failure and success cases. We see that SAM has difficulty with complex structures, such as the building complex in the top left of the figure. Here, SAM is able to segment individual buildings, but fails to grasp that the complex is one large structure. We see SAM fail in these cases where different objects are connected, such as in the building example, and in the roads dataset, where there are large networks of roads. We also see failure when the boundary between objects is unclear or difficult to make out, such as the crop dataset, where large plots of land are separated by dirt roads, or in the building segmentation, when the image is taken at an angle or there is a large amount of shadow. We see SAM excel when the objects have clearly defined boundaries and are compact, such as is common in the solar dataset. In the original SAM paper, the authors explore using SAM as an interactive annotation tool. SAM's output can be refined by providing additional prompt points after each segmentation output to reduce regions of error. This makes it ideal for human interaction to provide feedback on SAM segmentation. We replicate the experiments performed in the SAM paper with our datasets to determine if SAM can be used in interactive annotation of satellite imagery. For these experiments, we again use 3 different Prompt types. Random and center point prompts are selected in the same manner as before, with the exception of the mask, with the greatest IOU being chosen instead. We do this to simulate a human annotator choosing the best mask output. After the output from each single point prompt is generated, we select the next prompt point from the largest region of air in the output mask, and then refine SAM's output iteratively. We also evaluate SAM with a bounding box prompt taken from the ground truth. This is again to simulate a human annotator providing an ideal bounding box prompt. The bounding box prompts were not tested iteratively. We found that SAM outperformed our ITM, the state-of-the-art model SAM was compared to in the original paper. In all datasets, initially, and the difference tended to diminish as a greater number of prompts were taken. Plotted here is the center single point prompts for the SAM and our ITM. We see that SAM performs well for most datasets and achieves very high IOUs with only 4 to 7 prompts, the exception being Deep Globe Roads, where both models struggled. When comparing a single iteration of the interactive annotation experiments, we see that the bounding box prompts performs very well and wins out in all but 2 datasets. Again, we see that there isn't much difference between random and center point prompts, suggesting that SAM would be robust to variations of human input for prompting. In conclusion, we find that SAM performs reasonably well in automatic zero-shot segmentation, but will likely need to be fine-tuned to be more useful in overhead imagery. We also find that SAM performs very well in the human annotation experiments, and that has high potential for being used as an out-of-the-box annotation assist tool. Thank you.